I'll be giving a course of lectures on Einstein and special theory of relativity. My email address is given at the bottom, ajoykghatak at gmail.com. The course of lectures will be based on my book on Einstein and the special theory of relativity, which has recently been published by Viva Books in New Delhi. Of course, there are numerous books in this area, but the four most relevant books that I thought will be one by Ralph Berlin. The title is Newton to Einstein, The Trail of Light. It's a very easy to understand book published by Cambridge University Press. Then there is a book on revolutions in physics by Casper and Noer, and that is also very nicely written. And then, of course, there is the famous Feynman lectures on physics, which deals very authoritatively with the special theory of relativity. And then there is an edited book by John Stachel on Einstein's miraculous year, 5 papers that changed the face of physics. This book has a commentary by John Stachel on the various contributions made in those 5 papers, and also a reprint of those papers, the English translation of these papers. This book was originally published by Princeton University Press and has been reprinted in India by a company in New Delhi. In 1999, Albert Einstein was named Time magazine's Person of the Century. There were many nominations for this recognition, many of them, but the person who was chosen as the Person of the Century was Albert Einstein. I thought you would be interested to know that 3 finalists were Franklin Roosevelt, who was at one point of time the President of the United States, for triumph over freedom, over fascism and communism. Here is a photograph of Franklin Roosevelt signing the declaration of war against Japan on December 8, 1941, shortly after the Pearl Harbor attack. Then another finalist was Mahatma Gandhi as the embodiment of human rights and the creed of non-violence. The dictionary meaning of the word creed is faith or belief. That means and his belief of non-violence. This photograph shows Mahatma Gandhi at the end of the famous Salt March on 5th of April, and his handwritten note in which he wrote that I want world sympathy in this battle of right against might. And then was the finalist was Albert Einstein for his contributions in science and technology. And of course, the Time magazine choose him as the person of the century. And it is said that in a century dominated by science, he was the embodiment of pure intellect. He was the genius among geniuses who discovered, merely by thinking about it, that the universe was not as it seemed. So today we will discuss one of the many contributions of Einstein, and that was the special theory of relativity. It is widely believed that Albert Einstein was not a very good student, but he was a very good student. This photograph shows his school leaving certificate dated 3rd October 1896, when he was about 18 years old, and the certificate shows that he scored the highest grade in physics, algebra, geometry, descriptive geometry, and history. So he was a very good student, but he did not like the rigid educational system that prevailed in his school. After graduating, he became a teacher in a polytechnic, but he could not get a permanent position. So finally, he joined the patent office as a patent clerk, where he worked in isolation. And in the year 1905, Einstein, while working at the Swiss patent office, published 5 outstanding papers. These 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning miracle year, and therefore the year 1905 is known as the Einstein's year of miracles. In this miracle year, as I mentioned, he published 5 outstanding papers. The first paper was actually his doctoral dissertation that he submitted to University of Zurich, in which he described a method for measuring molecular dimensions. The second paper was a revolution in which he showed that light can be described consisting of packets of energy, quanta of energy. The concept of light quantum was introduced by Einstein in 1905. This light quantum eventually came to be known as the photon. The third paper was describing the theory of Brownian motion. The fourth paper was on special theory of relativity, and in the fifth paper, Einstein derived the famous E is equal to mc². So the first paper, as I mentioned, was on a new determination of molecular dimensions, which was part of the PhD thesis at University of Zurich. The second paper, Einstein proposed that radiation can be emitted or absorbed only in discrete amounts called quanta. And in the third paper, again published in Annalen der Physik in 1905, Einstein wrote, "Bodies of a microscopically visible size suspended in liquids must, as a result of thermal molecular motions, perform motions of such magnitudes that they can be easily observed with a microscope. The fourth paper, published on June 30, 1905 in Annalen der Physik, came to be known as the special theory of relativity, and the fifth paper, published on September 27, 2005, Einstein developed the famous equation E is equal to mc². All these 5 papers have been reprinted in this book, which has the title as Einstein's Miraculous Year. And let us read the title very carefully. It says, 5 papers that changed the face of physics. And the book has been edited by John Stachel, as I mentioned earlier. It not only reprints the English translation of the original papers, but also gives a commentary on the physics behind all the papers. Many feel that each of these papers was worth the Nobel Prize. In the foreword of this book, which has been edited by John Stachel, Roger Penrose, a very famous physicist, writes, "In the 20th century, we have been greatly privileged to witness 2 major revolutions in our physical picture of the world. We have come to use the term relativity to encompass the first of these revolutions, and quantum theory to encompass the second. It is particularly remarkable that a single physicist, Albert Einstein, had such extraordinary deep perceptions of the workings of nature that he laid foundation stones for both of these 20th century revolutions in the single year of 1905. Isaac Newton is considered one of the greatest scientists, and his annus mirabilis was the year 1666, when he was only 23 years old. In 1666, there was a plague in United Kingdom, and he was sent away from Cambridge, and he worked in isolation. And in 18 incredible months, the whole of 1665 and early months of 1666, Newton wrote down his famous laws of motion, explained the laws of gravity, discovered calculus, and developed a theory of optics. On the top left-hand corner, on the top figure is his Principia, and the bottom figure is the cover of his book on optics, in which he put forward the corpuscular theory of radiation. Isaac Newton was this painting was when he was 47-year old, and this photograph of Einstein on the right is when he was 26-year old, when he was working at the patent office in his annus mirabilis year. Many felt that the achievement of Isaac Newton could never be equaled by anyone else until Einstein in 1905 obtained results which were as revolutionary as that of Newton. However, the inverse square law, which was first suggested by the French physicist Ismail Biot, but put on a firm basis by Isaac Newton after Robert Hooke communicated this in a letter to Newton. Isaac Newton used the inverse square law to describe planetary motion without giving any credit to Robert Hooke. Hooke later accused of plagiarism. So, what I was trying to say is that although Isaac Newton and Albert Einstein both were great physicists, made tremendous contribution to the development of physics, but as a human being, I personally feel Einstein was a far better human being than Isaac Newton. There was a very bitter controversy. Not only he did not give credit to Robert Hooke, but also there was a bitter controversy regarding the discovery of calculus between Isaac Newton and Leibniz. Apparently, Leibniz had also discovered calculus independently, and Newton did not want to acknowledge that. Even the particle model of light was first put forward by René Descartes much before Newton, and he derived the Snell's laws using his particle model, and Newton did not give any credit to the work of René Descartes. Nevertheless, both of them were outstanding physicists. William Weston, who was Newton's successor as Lucasian Professor of Mathematics, wrote of Newton in his memoirs that he was of the most fearful, cautious, and suspicious temper that I ever knew. On the other hand, when Professor Bernard Cohen interviewed Einstein in April 1955, just about 2 weeks before Einstein's death, he wrote, "As I walked out to the street, I thought to myself that of course I had known that Einstein was a great scientist, but I had no idea of the warmth of his friendly personality, his kindness, and his rich sense of humor." Walter Isaacson, in his famous book on Einstein, has written, "Even as his fame increased exponentially, Einstein's fame increased exponentially, Einstein would retain a personal simplicity, an unaffected style, and at least a veneer of genial humility." The dictionary meaning of the word veneer is coating, and genial is, of course, gracious. So he would always have a humility in him whenever he spoke to anyone else. So let us discuss some physics. This is the electromagnetic spectrum, visible part of the electromagnetic spectrum. On the left hand side is the violet color, which has the smallest wavelength and highest frequency. And as you go towards the red color, the wavelength increases and the frequency decreases. So the red color is associated with a smaller frequency than that of the blue color. Similarly, the wavelength corresponding to the yellow color lies somewhere in between. Now, each atom gives out certain wavelengths which are characterized by certain frequencies, and this is known as the spectrum of the atoms or molecules. By carefully measuring the spectrum of atoms, one can figure out what kind of atom is there which is leading to this kind of spectrum. So the spectrum of an atom is a signature of the atom, and one can identify different atoms by studying the spectroscopy. Now, as we all know, our galaxy consists of hydrogen atom, and hydrogen atom has very discrete frequencies that it emits. However, if the atom is moving away from us, then the frequency observed will be slightly less. We say that the lines are slightly redshifted. This shift is known as the Doppler shift, which occurs due to the motion of the atoms. On the other hand, if the atom is moving towards us, then the frequencies become slightly higher, and we say that the frequencies are slightly blue shifted. So by measuring the shift of the spectral lines, one can find out whether the atom is moving away from us or moving towards us. In fact, by studying the Doppler shift of spectral lines, one can figure out, one comes to the conclusion that most of the galaxies are going away from us, are receding from us. In, in the energy of a photon, as we know, and this equation was first given by Einstein, is proportional to the frequency, and the constant that appears is known as the Planck's constant, h. And h has a value of 6.6 into 10 to the power of minus 34 joules second, and the momentum of the photon is given by h nu divided by c, where c is the speed of light in free space, which has a value of 3 into 10 to the power of 8 meters per second. So, this is the Doppler shift that I was talking about. As you can see, most of the lines get shifted towards the, have been shown to shift toward the right, towards the red. This shift in the spectral lines result towards the, is due to the motion of the atoms. And indeed, by measuring the shift in the spectral lines, one can calculate the velocity with which the atom is going away from us, the velocity of the galaxy. Let me consider the following experiment. There is a, I am inside a moving train, and the train is moving with a velocity u, let us suppose 100 kilometers per hour. Now, I am inside it. This frame is, we call it as S prime. There is an atom which is sitting at rest, and it emits 2 photons. Each photon is of frequency nu naught in opposite direction. So, that atom is at rest and it emits 2 photons, each having a frequency nu naught. So, the energy carried by each photon is h nu naught, so that the change in the energy of the atom, the change in the energy of the atom in the S prime frame, in my frame, this is equal to 2 times h nu naught. Now, each photon has a momentum is equal to h nu naught by c. However, one photon is moving in the plus x direction and the other photon is moving in the minus x direction. So, the 2 photons have equal and opposite momentum, and therefore, the total momentum carried by the 2 photons will be 0, plus h nu naught by c minus h nu naught by c. So, that the change in the momentum of the atom will be 0. And so, therefore, the atom which was at rest before the emission of the 2 photons will remain at rest after the emission of the 2 photons. So, a person on the platform who sees the train moving with a certain velocity u will see the atom moving with the same speed u before and after the emission of the 2 photons. Now, let us see what frequencies will he see. So, let me go to the next. So, I have here once again, this is inside a moving train, there is an atom. So, there is an observer here, say A2. Now, for him the atom is moving in this direction with a velocity u. So therefore, for him the atom is moving towards him, and so therefore he will see a blue shifted frequency, and the value of this frequency will be nu 2 will be equal to nu 0 1 plus u by c divided by 1 minus u by c. On the other hand, the photon that is emitted in this direction, the observer A1 will see the atom moving away from him, and therefore the frequency that he will observe will be a red shifted. That means the frequency will be slightly smaller, and this will be 1 minus u by c divided by 1 plus u by c. At the end of this course of lectures, I will derive these two expressions, but right now we will assume this. These are the expressions for the Doppler shifted frequencies when the atom is moving towards the observer and when the atom is moving away from the observer. So therefore, the moment as observed on the platform, the momentum of this photon of this photon that A2 observes will be higher than the momentum that is observed by A1. So there is a net momentum in the forward direction, but the atom is moving with the same velocity, and therefore for the conservation of momentum, its mass must decrease. I repeat, for the person on the platform, the photons have different frequency. In fact, the photon that is moving in the forward direction is observed at a higher frequency than that which is observed by A1, and so therefore there is a net momentum that is carried by the two photons in the forward direction, but the atom is at rest inside the train before and after emission. So it moves with the same velocity before and after emission. So therefore, for conservation of momentum, its mass should decrease. So therefore, whenever light is emitted from an atom, its mass must become slightly smaller. This was the famous statement made by Einstein in his 1905 paper. Let me explain this, that let us consider the simplest of the atom, the hydrogen atom. The hydrogen atom consists of a proton and an electron, say, circulating like this. We are saying, let us suppose the simplest Bohr model. So this is my positive charge, and then there is a small there is an electron negatively charged. Now when it is circulating in a larger orbit, and when it makes a transition and emits a photon, the atom still consists of one proton and one electron. The electron which is circulating at a larger radius goes over to an orbit of smaller radius, but in the process it emits a certain amount of energy in the form of a photon, and so because it has lost a little bit of energy, its mass must decrease. So light carries mass with it. So let me go back to the slides. So I have here, as I was telling, that there is I am in the reference frame S prime, I am B, there is an atom which is sitting at rest, and it emits two photons of equal frequency, of the same frequency nu naught. So, therefore, the change in the energy of the atom in the S prime frame will be equal to 2 h nu naught. On the other hand, the momentum of this photon is minus h nu naught by c. The momentum of this photon is plus h nu naught by c, and so therefore, the change in the momentum in the S prime frame of the atom will be 0, because the photons carry equal and opposite momentum. So, the atom will remain at rest even after the emission of the two photons. In the reference frame of the platform, which sees the train moving, there are two observers, one A1 and the other A2. Now, for A2, the atom is moving towards her. So, A2 will observe a blue shifted frequency, and as I mentioned earlier, I will derive these expressions near the end of my lectures, but let us take these expressions for granted. These are rigorously correct expressions. If the atom is moving with a velocity u, and c, as we have said earlier, is the speed of light in free space, then the frequency that will be observed for an atom moving towards the observer is nu 0 into 1 plus u by c divided by 1 minus u by c. On the other hand, for A1, she will observe that she will find that the atom is moving away from her. So, therefore, she will see a red shifted frequency. The frequency will be slightly less. So, nu 1 will be nu 0 under root of 1 minus u by c divided by 1 plus u by c. So, the change in energy in the S frame will be h nu 1, this is the energy of this photon that is coming towards her, plus h nu 2, and if you add these two numbers, a very elementary calculation tells us that this is 2 h nu naught by 1 minus u square by c square. Now, because the two frequencies are slightly different, the momentum carried by this photon as seen by A2, as seen in the reference frame S, will be slightly higher than the momentum seen by A1. And so, therefore, there is a net momentum which is carried in the forward direction, and this momentum is equal to h nu 2 by c minus h nu 1 by c, and if you do the elementary algebra, it comes out to be 2 h nu naught by 1 minus u square by c square under root multiplied by u by c. Since there is a net momentum which is carried in the forward direction, so therefore, the mass of the atom should slightly decrease, and in the S frame, let us suppose the change in the mass, the decrease in the mass of the atom is denoted by delta m. So, the change in the momentum will be delta m s multiplied by u. So, this will be equal to so much. This expression 2 h nu naught divided by 1 minus u square by c square is the change in the energy in the S frame. So, you get the equation. So, we just now derived that delta ms, this is the change in the momentum, it multiplied by u is equal to 2 h nu naught by under root of 1 minus u square by c square multiplied by u by c square. And we had shown earlier that the change in the energy of the atom as seen in the S frame, the frame of the platform is 2 h nu naught by 1 minus u square by c square. So, this quantity is delta E s times u by c square. So, if I equate these two expressions, the u's I can cancel. So, I get delta E in the S frame is equal to delta m in the S frame multiplied by c square. So, delta m in the S frame is equal to delta E S frame c square. So, delta E is equal to delta m c square. So, since these need not be infinitesimal, we have never assumed that this is the change in the mass. So, the change in the mass is related to change in energy in the S frame multiplied by. So, change in energy is equal to change in mass multiplied by c square. So, what is then mass? You see, a naive definition will be the quantity of matter. But you see, the hydrogen atom in an excited state or in a lower state, in both cases, it consists of the same electron and the same proton. So, that the quantity of matter is the same, but it has a smaller energy, and so therefore, the mass is smaller. So, the correct definition of mass is that mass is a measure of inertia, of how hard it is to set a stationary object into motion or to stop or deflect a moving object. So, in his 1905 paper, in the fifth paper, Einstein derived this equation. Of course, his derivation was slightly different. E is equal to mc square, and he wrote, if a body emits the energy E in the form of radiation, its mass decreases by E by c square. The mass of a body is a measure of its energy content. This was one of the revolutionary statements made by Einstein in 1905. And almost immediately after submitting this paper, Einstein wrote to his very close friend Conrad Habicht, and he wrote, this is the German translation of his original letter, the principle of relativity in conjunction with Maxwell's equations requires that mass be a direct measure of the energy contained in a body. Light carries mass with it. The argument is amusing and seductive, but for all I know, the Lord might be laughing over it and leading me around the nose. If you have two magnets far away, let us suppose they each weigh exactly 10 grams. So, sum of the masses of the two magnets is say 20 grams. Now, you put them on a frictionless table. If the north pole is pointing towards the south pole, as I have shown in this figure, then they will attract each other and they will join together. Now, in order to pull them apart, you have to supply a little bit of energy. You have to do a certain amount of work. And so, therefore, the weight of the two magnets which are stuck together will be slightly less. It will not be 20.00 grams, it will be 19.99999. The difference in mass will be extremely small, but there will be a small change in the mass. So, this is known as the binding energy of the two magnets. You have to do a little bit of work to separate these two out. So, we consider the simplest nucleus. The simplest atom is the hydrogen atom, and the next in the periodic table is the deuterium atom. The deuterium atom, the nucleus consists of one proton and one neutron, and they are held together by very strong attractive forces. So, if you take the neutron and proton away from each other, their masses are known to a tremendous degree of accuracy, as I will show in the next slide. But if you put them together to form the deuteron nucleus, then they are stuck together because of certain attractive forces, and you have to apply a certain amount of energy to pull them apart. And therefore, as I have tried to show this in this diagram, that the mass of the deuteron, in which proton and neutron are stuck together, is slightly less than the sum of the mass of the proton and the neutron when they are far away. And this is known as the binding energy of the deuteron. So, the mass of the proton is 1.6726231 into 10 to the power of minus 27 kg. Mass of the neutron is also known very accurately, 1.6749286 into 10 to the power of minus 27 kg. But the mass of the deuteron, which consists of a proton and a neutron, is not the sum of the two. It is slightly less than that. And the mass is 3.3435860 into 10 to the power of minus 27 kg. And if you calculate what is known as the mass defect, that is mass of the proton plus mass of the neutron minus the mass of the deuteron, then it is a smaller mass, 3.9657 into 10 to the power of minus 30 kg. And so therefore, the binding energy of the deuteron nucleus, if you multiply by c square, it comes out to be 3.569 into 10 to the power minus 13 joules or 2.23 MeV. So that is the binding energy of the nucleus. But the most important thing that I have tried to show is that the mass of the deuteron nucleus, which consists of a proton and a neutron, is slightly less than one proton and one neutron weighed independently. In fact, it takes a gamma ray photon of 2.23 MeV to split the constituents of the deuteron nucleus. So, it separates the two particles, proton and neutron. So, it requires a 2.23 million electron volt gamma ray photon to split the deuteron to a proton and a neutron. This is known, as I mentioned earlier, as the binding energy of the deuteron. Even in the fission process, which occurs in a nuclear reactor or an atomic bomb, when the neutron is absorbed by uranium-235 nucleus, one obtains an excited state of uranium-236 nucleus, and the model that describes it is known as the liquid drop model, and it can under certain circumstances split into two smaller nuclei. One example could be barium and krypton, and in the process 2-3 neutrons are emitted. But the main thing is that the barium and the krypton nuclei are very tightly bound, and so therefore a loosely bound system goes over to a tightly bound system, and in this process a certain amount of energy is released. This energy is approximately about 200 million electron volt, and this is the fission energy that is liberated as a consequence of the small loss in mass that occurs in this fission reaction. In the uranium bomb that was dropped on Hiroshima on 6th August 1945, energy equivalent to about 13 kilotons of TNT was released, and only about half a gram of matter was completely converted into energy. So therefore, in the explosion that occurred on Hiroshima, only half a gram of matter was completely converted to energy. The other type of nuclear reactions that are extremely important are known as fusion reactions. And one example is that you have a deuteron nucleus, you have a tritium nucleus. The deuteron consists of a proton and a neutron, and the tritium consists of proton and two neutrons. And they fuse together and they produce one neutron and one alpha particle. And the alpha particle consists of two protons and two neutrons. So, as you can see from the diagram, the number of neutrons and number of protons before the fusion reaction is the same as those after the reaction is over. But in the process, the fusion reaction makes a very tightly bound alpha particle, in which the particles are very tightly bound. So, it has a very large binding energy, and so therefore, a significant amount of mass gets converted to energy. And in this case, no light is emitted. This energy appears as kinetic energy or heat energy of neutron and that of the alpha particle. So, this is the energy that is released about in this particular fusion reaction, about 17.6, as I have written. In a typical fusion reaction, deuterium and tritium fuse to produce a neutron and a very tightly bound alpha particle. In this fusion reaction, there is a small loss in mass which appears as kinetic energy of the neutron and of the alpha particle. And in a fusion bomb, such reactions occur, resulting in a tremendous release of energy. As you know, the energy coming from the sun is due to the fusion reactions that are occurring inside the sun, and we receive light, electromagnetic radiation from the sun. If we put a plate of 1 meter by 1 meter at the top of the atmosphere, we can find out how much energy is crossing that area per second. This energy is approximately 1350 joules. That means 1350 joules of energy is crossing 1 square meter per second. This is the energy that we receive from the sun. So, in this diagram, I have tried to show the earth here, and I have a 1 meter by 1 meter plate, and that receives 1.35 kilowatts per square meter. The distance of the sun from the earth is about 150 million kilometers, which is 1.5 into 10 to the power of 11 meters. So, this is the energy. 1.35 kilowatt is the energy that is received on 1 square meter of area. So, the total energy liberated by the sun will be equal to this multiplied by the surface area, which is 4 pi r square. And if one did the elementary algebra, then one finds that the total energy liberated by the sun is about 4 into 10 to the power of 26 joules per second. So, this is an enormous amount of energy that is released every second. And if you now calculate how much mass is getting converted to energy, so this will be delta m is equal to delta E by c square. So, the energy that is getting received, that is being liberated by the sun, is 4 into 10 to the power of 26 joules per second. The speed of light, as I mentioned earlier, is 3 into 10 to the power of 8 meters per second, and if you divide this by this, you will get 4 into 10 to the power of 9 kilograms per second. Thus, the sun, from the sun, every second 4 billion kilograms of mass is getting converted to energy, and this energy, part of it, a very small part of it, we receive on the surface of the earth. So, if you ask me the question that is the mass of the sun decreasing, the answer is yes, the mass of the sun is decreasing, and in fact the size is not decreasing. In fact, the size is increasing, because the gravitational force to hold the together is decreasing. So, as we all know, as the astrophysicists tell us, that in fact the loss in mass is resulting in the earth becoming in the sun becoming bigger, eventually in about a, but the fractional change in mass is extremely small. However, in about a few billion years, 10 to the power of 9 years, the sun is expected to become a red giant and probably engulf the earth itself. So, the thing that the important result that we have derived in our calculation today is that that the sun, the mass of the sun is decreasing at the rate of 4 into 10 to the power of 9 kilograms per second. So, every second about 4 billion kilograms of mass is continuously getting converted into energy. Thus, every year about 120,000 trillion kilograms of mass is continuously getting converted into energy in our sun. There is a very nice book which does not have any equation other than E is equal to mc square, and the title of the book is E is equal to mc square, a biography of the world's most famous equation. It is written by David Bodanis, and in the preface of the book, David Bodanis writes, this is a photograph of the actress Cameron Diaz. A few years ago, I was reading an interview with the actress Cameron Diaz in a movie magazine. At the end, the interviewer asked her if there was anything she wanted to know, and she said she would like to know what really E is equal to mc square means. They both laughed. Then Diaz mumbled that she had meant it, and then the interview ended. You think she did mean it? One of my, David Bodanis writes, one of my friends asked. After I read it aloud, I shrugged, but everyone else in the room was adamant. They knew exactly what she intended. They wouldn't mind understanding what the famous equation meant. So, here I have tried to tell you. So, E is equal to mc square is considered as one of the most, not only one of the most important equations, but one of the most famous equations that everyone wants to know the actual meaning of. I hope I have been able to tell you the meaning, the consequences of the equation E is equal to mc square. In fact, this is a E is equal to mc square sculpture in Berlin on the occasion of the 2006 FIFA World Cup in Germany. As I mentioned that in a fusion reaction, a loosely bound system goes over to a very tightly bound system, and energy is released. In this slide, we have shown that 4 protons combining to give one alpha particle, which consists of 2 neutrons and 2 protons, and to conserve charge you have to have some negative charges, electrons that come out. This is not the way the reaction occur, but it is in a series of catalysts that are there which result in the final equation is that the 4 protons get converted to an alpha particle and electrons, 2 electrons and some neutrinos and things like that. And in the process, this is a fusion reaction. In the process, certain amount of energy is released. In fact, Hans Bethe received the 1967 Nobel Prize in Physics for his discoveries concerning the energy production in stars. And I had the great privilege of learning quantum mechanics from 2 great outstanding persons, one Professor D.S. Kothari at Delhi University and Professor Hans Bethe at Cornell University. So, you have this equation that delta E, the change in the energy of the atom in the S frame, if I write that as change in mass in the S frame times c square, and the change in the energy in the S prime frame, I write as change in the mass in the S prime frame in c square. We had earlier derived that the change in the energy in the S prime frame, where the atom is at rest, is 2h nu naught. The change in the energy of the atom in the S frame is 2h nu naught by 1 minus E square by c square. So, therefore, this, the numerator is delta E time in the S frame, S prime frame. So, delta m s, the change in the mass in the S frame is change in the mass in the S prime frame divided by 1 minus u square by c square. Since these need not be infinitesimal account, so we get the velocity dependence of mass, that the mass as seen, if the atom is moving with a velocity u, then the mass that is observed by a person on the platform will be m naught is equal to divided by 1 minus u square by c square. I think we end today's lecture on that equation, and thank you.